All right, as promised, let's redo that same problem with Lagrange multipliers. Now, first thing to note is that we have this constraint. But if we look at the method of Lagrange multipliers, the constraint must be equal to 0. There is no other way to do it. We have to set it equal to 0. That's key. Okay, so I'm going to take my constraint function. I'm going to rewrite it as x squared y squared minus 4 equals 0. And we're going to make a little note right now, right? Must equal 0. Star it, right? All right, so this is now a function, our constraint function. It's g of xy. So g of xy is x squared y squared minus 4, and we're going to set that equal to 0. All right, now, how does the method of Lagrange multipliers work? Well, remember, it says the gradient of f is equal to lambda times the gradient of g. All right, so let's set up the Lagrange multiplier. So that would be that the gradient of f is equal to lambda times the gradient of g. Now the gradient of f is f sub x, f sub y, which is lambda times g sub x, g sub y. No problem. All right, so let's look at f. The derivative of this with respect to x would be y plus 1. So y plus 1, comma, f sub y would be x plus 1 equals lambda times the derivative of g with respect to x would be 2x y squared, and then 2y x squared, or 2x squared y. And the derivative of 4 is 0, so that just goes away. Okay, now, how this has to work is if these things are going to be equal, then the x component has to be lambda times this x component. So you know y plus 1 has to be equal to lambda times 2xy squared. And at the same time, I could take the y components. Let me see here. This component, x plus 1 equals lambda times 2yx squared. So in other words, if I solve this for lambda, lambda is y plus 1 over 2xy squared, and lambda is x plus 1 over 2yx squared simultaneously. Now, since these two things have to be equal to each other because they're both equal to lambda, that means that putting it together, y plus 1 over 2xy squared must be equal to x plus 1 over 2yx squared. And we can solve this for x and y. And I'm just going to use Maple to solve it. We can do algebra. It's not actually that tricky. Here, I'll do the algebra real quick. So if I multiply everything, if I cross multiply, I'd end up with y plus 1 equals 2, or excuse me, y plus 1 times 2yx squared equals x plus 1 times 2xy squared. I divide everything by 2xy because they all have that in common, and that'll leave me y plus 1 times x equals x plus 1 times y. And the only way that's going to happen, so this is xy plus x equals xy plus y. Subtract the xy, subtract the xy. These are gone, and you're left with x equals y, which sure enough is exactly what would happen if I went and stick it into Maple. So let's see here. I told it my constraint function, and then I had it find the gradients just to double check myself. And then I said, hey, set these two equations equal to each other and solve it for x and y. And sure enough, it tells me that x is equal to y, right? And y is equal to y. Okay, so then if x is equal to y is the solution, what am I going to do with it? So we're going to take x equals y and we're going to substitute into the constraint. So this, believe it or not, is an answer. so we're going to take x equals y. Let me think where I'm going to put it. I'm going to put it over here. And we're going to substitute into g of xy. Equals 0, or excuse me, yeah, g of xy equals 0 and solve. Okay, so g of xy was x squared times y squared. So if I make it so that x is equal to y, it'll be g of y, which is y squared times y squared minus 4. So that would be y to the 4th minus 4. And if that's equal to 0, that means y to the 4th equals 4. So y, if I took the 4th root of that or took the square root of that, I would have the square root of 2. Plus or minus, of course. Right? 4th root of 4 is the square root of 2. And if you don't believe me, of course, I did it in Maple as well. And I said, okay, evaluate that constraint function with x is equal to y. And sure enough, it came up with y to the 4th minus 4. And then I said, evaluate setting that equal to 0. So I set my constraint function equal to 0 and solve it for y. And it comes up with square root of 2, negative square root of 2, and then these two imaginary answers that we don't care about and are not going to use. So we can ignore those two. All right, then to get your x's to go with it, you just say, well, let's think. If x squared, well, if x is equal to y, let's put it that way. So if I know that x is equal to y and I know what y is, so putting these two together right here, this fact and this fact, I get my critical points, right? So this goes together with this, and I know that I have square root of 2, and negative square root of 2, negative square root of 2. Now, you actually don't really have to show this by hand work here if you can get Maple to solve it for you, of course, right? So you can kind of bypass all of this, right, and Maple will solve it. But it's not particularly difficult work to do. That's the advantage of the Lagrange multiplier method, is sometimes the work to solve them is actually pretty easy. So, and this was pretty easy. All right, then all we have to do is make our little table. So we set up the Lagrange multipliers, we solved, I should say. So we set it up here, and then here we started solving. Right there, right? So we started solving all of this, got here, and now we just have to make the table. And compare values of critical points, I should say. All right, so let's do that. So all right, so our critical points are square root of 2, square root of 2. This is looking very familiar. And negative square root of 2, negative square root of 2. We already know what this is, of course, because we did it on the previous problem, but that's not the point. All right, so then we find f of x, y, which we already did again. This is 2 plus 2 square root of 2. This is 2 minus 2 square root of 2. So that means that we have an absolute min. So this is our conclusion that we would draw down here. We have an absolute min at negative square root of 2, negative square root of 2, 2 minus square root of 2. And we have an absolute max at, let's see here, square root of 2, square root of 2, 2 plus 2 square root of 2. There's our max. And there's our min, and we found them, but in a different way, right, using a different method. And sometimes the method is easier, sometimes it isn't. Usually it is. Usually the Lagrange multiplier method's a little bit easier. And that's the advantage to it.